All right, welcome to another session of DGX Compare. This is a follow-up test. We're working on Nemotron 3 Super today as a follow-up to our July efforts. Nemotron Super is a 120 billion parameter model by NVIDIA, quantized down to NVFP4. And it's currently installed on a cluster of DGXs. The left is a DGX Spark, and the right is a Acer DGX GN100. They're clustered together via CX7 QSFP connectors. They're each by default 273, I think, gigabytes per second native, but because of the connectors, that speed gets dropped down to around 200. So it's not going to be as fast as something that's a solo, I guess, a single node with a lot of memory. But they come with 128, so 256, you have to do a cluster. Now, the follow-up from July is important because when we ran this model in July, the token speed, the token generation speed, or token per second, with a cluster was very similar to the speed on a single node. And that wasn't too surprising for us. But what a lot of people have said is that it can actually be faster because we can set certain parameters when you're doing the clustering to improve performance. And so since then, we've actually tried that. And today is going to be the experimentation of what happens when you improve on vllm parameters. So same as before, the top activity monitor is for the DGX Spark, and the bottom activity monitor is for the GN100. Our query today is the same one as last time. Tell me all about Tyrannosaurus Rex with Tyrannosaurus misspelled. There we go. Let's watch that over there and that over there, and you can see CPU activity. So it's starting to get busy. Not messy yet, but busy. So this is the thinking model. Let's actually open up its thinking and thought process. It's thought for, it looks like 13 seconds for RAG, and it's still thinking for knowledge bases. 10 seconds there. I'm actually going to turn that off for the second test. I actually don't want to be doing any kind of RAG. I think that setup was from earlier where we were actually testing ingestion, but it's finished thinking and that's the tokens. Let's see how it goes. So this looks like a solid token speed. That looks about 40 maybe, 35, 40. When it's 50, it goes a lot faster straight. One thing we really like about the Nemotron models is the amount of detail that it provides, especially with the formatting like this. It's really nice and good to read. Let's see how the cluster is working. It's pretty stable, 127. Nothing's going to swap yet. Over here, 128. It's busy, but not too messy yet. And here it's consistent. So it's still drawing. It's got byte force, paleobiology and behavior. And we really like the Nemotron models, especially for this this prompt, because if you look at our other videos, when you do the same query on other models, sometimes you get a page and a half maybe, and it doesn't have the detail that this model has, at least for this kind of query. It really shows the amount of effort that NVIDIA is putting in to really making their models. I think this model was shrunk down from the Ultra. That Ultra was, I think, 550. This is 120, and then NVFP4 quantized down. And I can't remember what the active number of parameters is. I'll paste it into the description later. But the router for its this mixture of expert model is pretty good. It gets the correct amount of data and the detail that's expected. And sometimes it even throws you this cool little green icon or an avatar of a Tyrannosaur or a T-Rex. So yeah, it's pretty consistent at 3540. I'd say it's closer to 35 than it is to 40. Cool. So that completed. It's still pretty busy, but we can kind of see that die down. We're waiting for it to do the follow-up, and that's when it really shuts down. There we go. And this should start to drop down, at least some of it. See that drop after the end. Let's do a follow-up. What evidence exists for feathers? All right. Heat is still okay. Because I have all these fans running, I can't really tell or hear the fans going from the actual devices themselves. But usually the temperature will give us a hint on how hard it's running, and right now it's okay. It's still thinking, and again we had that rag feature on, so we'll turn that off. Here's decode after prefill, and yeah, it's definitely 35. It usually gets slower as we tend to use more memory. I mean, we're at 98% now here, 99% of memory being used, and 97.5 over there. So we're at the edge, I guess. And look how messy it is over here on core usage. So yeah, it's definitely working hard. And what I'm really paying attention here for are gibberish characters or repeated text. It's called looping, but I haven't seen it yet. If you guys want to see looping, check out one of our other videos. It happened with, I can't remember the model. I think it was, I'll list it out in the comments below, but yeah, we had a model where it was all looping. Yeah, this is definitely solid. By far, this and the DeepSeek provide the most detail when you, okay, no, I thought it was duplicate information, but it's not, it's actually different. But they provide the most detail when it comes to something subjective like this. And when I say subjective, it's a different result each time. It's not necessarily deterministic. Let's give it a look. I'm pretty satisfied with the token's speed and stability in a single chat. Cool, that completed. See the drop there. And some have dropped as well. We're just waiting for the follow-up. It'd be interesting to kind of see how this works with RAG. So again, a follow-up test. We'll do 2 more tests. We'll do one video with no RAG at all, and another one with actual RAG. I'm pretty satisfied. Let's check it out with tools. So our typical test will be involved in opening up this 18K file. I'm gonna grab the query. This is a small file, small CSV file with automotive data. And what we're asking it to do is to open it, write and execute Python code and calculate the total number of rows and columns and some statistics off those rows and columns. We'll make sure we have the code interpreter on to do the Java script, to do the Python. And that's pretty much settled down. And let's give it a look again. CSV files, for those who aren't too familiar, if I opened up a flat file, a flat text file, 18K is it's fast. CSVs, however, get a little tricky because of the header and of course the commas, and what the ingestion process, what happens there is when they're trying to ingest the data to determine what the columns are or where the rows end, it takes a bit of processing. So even though it's a small file, 18K, if let's say the file was, let's say 100 rows, sorry, 100 rows with 2 columns, that's easier to process than if you say did 50 rows and 30 columns, because they have to, the Python has to go and take a look at all that information when they're doing the processing. Prior to that, during the ingestion process, the model still has to determine how many rows there are before it passes it on, right? So, sorry, not pass on, but before it executes it. So, yeah, that's what takes some time. Okay. So right now it's because we have that on, which is the ability for us to execute Python. It's actually saying exploring code. So it's thought for almost a minute now, and it's actually saying. Let's view the result from the execution. And that should be pre-fill. And now it's going to execute decode. I'll open up this thinking part to see what it's doing. So yeah, it's telling us what it's going to do. And it correctly found that it's 398 rows and 9 columns, which is really good. A lot of times when models run out of memory, it will say 3 rows and 9 columns. But in this case, Nemotron actually correctly identified the correct amount of rows and columns and gave us these statistics. I don't have it on memory right now, but let's do it really fast on Gemini. I'll do the same file. I wish I had this actually on a text file just to compare the results. But same query. And again, this will be really, really fast because we are working with a frontier model and with probably 1,000 times more processing power. But what we're trying to find out here is whether or not the results that were generated by Nemotron are accurate. So here's the code that it generated, and when it ran, 398 and 9, and the mean 2351, 545, 193, 104. Where's 104? Oh, that's horsepower. It's not here. 29, 70, 42, 1557, 76, 157. Yeah, it got everything that they listed out correctly. It didn't list that horsepower. And here's why. The horsepower and name columns are non-numeric and were excluded from standards calculations. I'm okay with that. You can probably get that query with a follow-up Python call. But the important part is that 1, it was able to ingest the data. 2, it was properly able to produce the data and demonstrate it by delivering it to the screen. And also for the data that it couldn't process, it actually showed it up on the screen. So wow, very impressive. Very happy with this model. Let me show you guys right now what exactly, I'll put this in the description for the vllm calls. But these are the main differences between what we did in July and what we did now. This is the big one, nickel IB disable. That helped a lot, and force eager also helped a lot. I think, yeah, we also changed the GPU memory utilization. I don't know why it was 55% before. I think we tried to get it, I think there was a bunch of things that were really slow, and now that's much faster. And I know that this one right here, nickel IB disable is equal to 1. And that's another thing that we put in. And also the big one, tensor parallel instead of pipeline parallel. So pipeline parallel is when you have multiple GPUs but on separate devices, and logically that's what you would choose. But then if you really think about it, when you're working with a cluster, the way NVIDIA set up these boxes, at least the way the playbooks had it, you're actually simulating a single GPU because of the cluster. And so it's as if it was 2 chips in a single box instead of 2 separate boxes. And running this tensor parallel call sped it up, right? Not by a lot, but it speeds it up enough so that it's noticeable. So anyways, oh yeah, one last thing. We spent some time on adding speculative decoding, which is kind of, guessing what the next couple of words are. And whatever combination that we did, it wasn't really improving it. And we confirmed that with the playbook at NVIDIA. And yeah, they still need to improve on that in future builds. So, but I'm pretty happy with this as is, right? I know you could probably increase the speed by another 10-15% if they can figure out the speculative decoding. But for now, I'd say 35 to 40 tokens per second. It's able to handle tooling. Yeah, I'm very impressed with the model and the improvements. Thanks a lot for watching. And again, Nemotron 3 Super 120B quantized NVIDIA NVFP4. Thanks for watching.